Measuring distances in space. Now, if you send a radar pulse to the moon, how long would it take to get there and back? So we can measure how far away the moon is using radar. And if we say time is distance over speed, the speed being the speed of light, then for the distance there and back, 2.56 seconds. You should learn a few assumptions. What assumptions did we make in this calculation? We assume that the speed of light is a constant 3 times 10 to the 8 meters per second. We assume that the distance between the Earth and the moon doesn't change in the time that we take the measurement, and we ignore the radii of the Earth and the moon. It's interesting that when Apollo missions went to the moon, they left some mirrors on the moon, which scientists have used to bounce laser beams off to measure the distance to the moon very, very accurately. Now, by taking repeated measurements of distance, we can calculate the relative velocity of an object. For example, if there was an asteroid approaching the Earth, if you measure the distance twice, and then the difference in the distance divided by the time between the measurements would tell you the relative velocity towards us. Bearing in mind it's not necessarily heading directly towards us. What we're measuring is the component of its velocity towards us. And in a situation like that, an asteroid heading towards Earth would be speeding up, gaining kinetic energy. So what we're actually measuring is the average velocity in the time interval between readings. Using radar measurements to measure distance has its limitations. Apparently you can use it to measure how far away Mars is and perhaps a few objects in the asteroid belt, but further than that, not really. Why? Because you're sending out a radar signal. The signal will get weaker and weaker the further it goes. A tiny fraction of that will be reflected back, and then the actual signal which gets back to Earth would be very, very, very weak. So there are limitations to using radar. Space-time diagrams I'll mention now. These have come up a few times in recent years. Don't panic, just look at the axes. It's like a distance time graph, only on its side. So as time passes, you're working your way up the graph. On the y-axis, you've got time in seconds. On the x-axis, you've got distance. And we say it's measured in light seconds. Well, 1 light second is 3 times 10 to the 8 meters, the distance light travels in a second. A line on the graph is called a world line. And any point on the graph is an event. It's a place in space and time. So the red line on the diagrams represents light, because light travels 1 light second every second. Light must be at 45 degrees. A stationary object, its world line would just be vertical, as it is on the first diagram. On the second diagram, if an object was moving away from us, then look at the blue line, that's its world line. And the red line there could be a radar pulse bouncing off the object. If a question comes up, don't panic. As I said, just look at the axes, and the question should be straightforward. Well, it has been in the past anyway. Other methods astronomers use to measure distance. You don't need to know a great deal about these. I'm mentioning them in passing. Heliocentric parallax. For stars which aren't too far away, within a few hundred light years, basically as the Earth goes around the Sun, we are looking at these stars from a different angle. And if you imagine the very, very, very distant stars are like the background wallpaper, and so there is a parallax effect, and the angle changes as we look at them 6 months apart, and measuring that angle you can work out how far away these stars are. For more distant stars and stars in nearby galaxies, we can use things called standard candles. If you imagine we know how bright a candle is, then if you look at a candle, then the further away it is, then the dimmer it is. So some stars, we know how bright they actually are. We know how much light they give off. And if we measure their brightness, we can work out how far away they are. And these types of stars, there's various ones. There's things called Cepheid variables and blue supergiants and type 1a supernovas. They're called standard candles. And then for distant galaxies, for the ones which aren't close to us, in my next video, I'm going to talk about redshift.